So we're going to get through 2 chapters today because they're so short. I'm excited. So we're going to talk about just like how to make an experiment, like what makes a good experiment. We'll talk about like the father of data science kind of. And then we'll talk about Python in general. That'd be great. So yeah, let me know if you have any questions about anything. Just shout out. I like to run these classes as discussions. But without any further ado, let's do it. So we'll talk about causality and experiments. So this is these slides are on chapter 2. So please start reading chapter 2. There's a bunch of important things I need to teach you. I'm required to teach you that come from this chapter. It's like all the first little terms that we got to know. So just in case you never heard of them before, to start, I have a question for us. There has been a study, a legitimate study. I think they did it in Switzerland, and they kept track of a bunch of people over time, some people who ate chocolate and some people who did not eat chocolate, and they kept track of how often or whether or not those people in their lives had like a heart attack, some heart issue. So it is legitimately true that those people in the study who regularly ate chocolate, with an 8% chance, they had a lower heart attack rate. 8% lower heart attack risk percentage. All right. So they had heart attacks less often, 8% less often than the people who did not eat chocolate. Crazy. That is a real study that is linked to that number. Insane. So my question to you then is, should we therefore be eating chocolate all the time? Like, do I need to have chocolate with every meal then? Or at least once a day? Why or why not? So please, if you want to discuss with your neighbors, go for it. But I'd like to have this discussion. Tell me what you're thinking. Maybe take a minute to formulate your ideas. Are you pro-chocolate now? This is legitimately true. 8% lower heart attack risk. Seems legit, right? It was a real study. All right. Any brave souls want to tell me their thoughts in their mind right now? Are you going to do it now? Are you going to eat chocolate if you don't already? I actually don't like the taste of chocolate that much. I don't have chocolate. So I'm going to die before all of you, probably. But maybe I should. Any thoughts?
I feel like this kind of linked to it doesn't mean it's probably the exact cause.
Good. Yeah, you kind of know where I'm going with this. It sounds like they proved the link. They didn't prove that it's the chocolate after all. Does that make sense to all of us? I think maybe there's a lot of other ideas that are at play here. Chocolate is that something you're kind of like everybody goes and buys every week? It's more of a commodity, right? It's something that's nice to have. It's something that if you have some extra money, you'll go and buy. So maybe people who have extra money, they go and buy chocolate as a treat for themselves. And people who generally make more money and therefore can buy chocolate, they usually have better health care. They usually have fewer hours at work. Some of them don't have to work. Does that kind of make sense? How maybe there is another idea going on at play behind the scenes. So what they proved in the study is something called an association, or maybe you've heard the word correlation does not imply causation. That's kind of where I'm going with this, if you know that argument already. But they said that they showed in the study there's a legitimate association or correlation between eating chocolate and reducing your risk of heart attack. But the question is, does that mean that it was the chocolate that caused it? Causation is the question of the day. Causation, question mark. And I want to say probably not. I think that people who eat chocolate are probably better off. They're higher class. People who can afford the chocolate, usually they have less stress at their work sites, and I don't know. That probably means they're not going to have a heart attack. It didn't have to be the chocolate. Something like that. That's my thought process. Okay, you could have a different thought process, but I think you can kind of see the way that argument could be knocked down a little bit. All right. Any questions about that idea? So maybe you don't have to eat chocolate every day. You just got to be rich. All right. So with that, let's talk about some terms. So, because I'm going to talk about a great example from this chapter too. If you've read ahead, it's a cool one. We'll talk about a very important man in data science. But here's a bunch of things you need to know. We're going to talk about these things. They're also part of the chocolate. The chocolate study. So the first one is observational study. So an observational study is when you give surveys to people who are already doing what they're doing. So that's when a scientist, they're doing their study, they're making conclusions based on data that they've retrieved, but they didn't take part in generating that data. And what I mean by that is chocolate eating was an observational study. They didn't ship chocolate to a random group of people and tell the other people to not eat chocolate. They just took a survey and were like, do you normally eat chocolate? Did you have a heart attack? So they were already doing what they were already doing. That's important because usually it's like when you're testing a drug, maybe you've heard of the term like randomized trial. That's like the gold standard. This was not that. This was an observational study where you observed some data, but you didn't generate that data. You didn't tell somebody to go get this COVID shot, and you didn't tell somebody else to get a placebo, and it wasn't random. So it's harder to draw causationality from that, okay? Causality is the word I'm looking for there. So sometimes all you can do are observational studies. We're going to see a data set later in this class that has to do with the weight of babies birthed to women who smoked and who did not smoke. You can imagine that would be an ethical nightmare to go and make a randomized trial for that. Like tell some pregnant women, oh yeah, I'm going to have you smoke for the duration of your pregnancy, right? You cannot do that. That's impossible. The only way that you're ever going to get any data on that is to have an observational study. Just go to women who are already, unfortunately, smoking during pregnancy. Does that make sense? So you can't draw as many conclusions from that, and I hope you see why. So there's that. Then also there's some key terms in all these studies. So individuals is going to be the name, like what they're calling the people involved or the things involved in the experiment. Because like maybe you're doing an experiment on mice, the individuals are the mice at that point. All right. So the individuals in this observational study on chocolate and heart disease risk, were about a little over 300,000 adults in the U.S. Sorry, it wasn't Switzerland. It was Sweden and Australia. Okay, so a lot of people, and so they found a strong number difference, but maybe it wasn't causation, right? So there's that. And then treatment, even though it's not a drug trial, all the studies, there is a treatment involved, and that's just the technical term. That's the thing that they're studying. It's the factor of interest. So the treatment here was chocolate consumption. It's like you can imagine like you're injecting chocolate into somebody. That was the treatment. You're having some people eat chocolate, some people didn't eat chocolate, and you're seeing what happened. That was the treatment. Did the treatment cause the outcome that we saw, kind of, is where we're going with that. So outcome is a word you probably know, but in terms of a study, it's what happened to the individuals based on the treatment. So what happened to the people who are eating chocolate? What did we study? What was the outcome? It was heart disease or not heart disease. Okay, I hope that makes sense. Yeah. Any questions about any of these terms? So you'll get used to them as you see them. But there's that. Those of you who came in, remember that we got attendance going, so please do attendance in the next few minutes. So we got that, and yeah, we noticed that there was an association between people eating chocolate and a lower heart disease risk, but we're not sure if there was causation. If eating chocolate actually caused them to not have heart attacks. There could be some other factors at play. That was the idea, right? We noticed what's called a negative association, because when chocolate consumption went up, heart disease risk went down. Do you see how they're not in lockstep? They're inverted. Sometimes when you if you ate chocolate, maybe some people, maybe some other disease goes up, like their likelihood of disease goes up. That's a positive association. A negative association is when you do one thing and one thing goes up, the other thing goes down. So there was a negative association between chocolate consumption and heart disease. Another word for association is correlation. So association, aka correlation, if I can spell. Which is cool to think about. It's worth trying. It's easy to eat chocolate. The question of the day, though, is did it cause it? Did eating chocolate actually cause that lowered heart disease risk or heart attack risk? That's called causality. That's when one thing really does cause another, and you know beyond a shadow of a doubt it happened because of that thing. Right? We can't quite prove causality for this trial, for this study, even though there are a lot of people involved, because there might be other factors at play. There was nothing that was randomized. There might be other factors at play, like income and things like that. They probably had access to better doctors, people who can afford to have chocolate all the time, things like that. Okay? So association or correlation is not the same as causation. Does not cause another thing. We saw that there was a link, but we're not sure if that was really the thing. Yeah.
Does causality have to be direct or can it be indirect as well?
Like a domino effect, like this thing caused this other thing, which in turn finally caused the thing I'm looking for. I would still call that causality, but maybe.
Or just like me plugging my phone causes it to charge.
Yeah, I would still call that causality. Mm-hmm. You don't have to talk about the electrons flowing. Like one thing really did lead to another at the end of the day. That's still causality. It happened because of that original thing. It was nothing else that could have possibly done it. It was you plug it in the phone. Yeah. No, that makes sense. Other questions? That's a good one. Yeah, so just shout out if you have anything that you want to talk about. I would now like to tell you the story of a man named Jon Snow with an H. So, not the dude from the very popular show. So, we've got, there he is. I want to tell you his story. He was like the father of data science. When you read this chapter, you'll get to hear this story all over again. It's a fun story, but it's a really cool one. It's a good reason to want to study this. So, back in London, people were getting sick. They were getting sick with cholera, and we know nowadays that cholera comes from bad water, like you're ingesting a bacteria, and it usually comes from contaminated water. That's what happened in London. All right. So nobody knew what was going on. Nobody knew what caused cholera, and Jon Snow was employed by, I think, the government probably to go and investigate this. All right. And so the very first thing he did was he took a map. He made a map. He made a little map, and he started drawing little rectangles next to houses where people got sick with cholera. Something people didn't do before. Like he invented this kind of diagram, which looks pretty cool. And so you can see that in this diagram, in this map, a lot of people were getting sick around the same spot, and then there were just some minor occurrences away from there. So again, he's trying to see what caused the cholera outbreak in London. Is there a way to link this and not just get association? All right, what was the real reason? Because they didn't know that it was the water yet. And so he made this map. He noticed that there was a hot spot around a particular water pump. And so back in the day, there was not like water running to everybody's house. You'd have to go out to the nearest water pump, like pump the thing, and that's what you got the water in, and you bring that back home, and that's what you do your cooking with or your washing with. And so it turned out to be this Broad Street pump that had the contaminated water because there was like runoff from like a butcher shop or something that somebody that was doing something not great got into the water supply there, but not anywhere else. And so this map caused Jon Snow to think like, okay, maybe it has to do with the water, right? Maybe it has to do with the water. There were other people getting sick around here in other places where they did have closer pumps, but apparently, you go read the story in the textbook. I forget the full details, but apparently some people they just really like the taste of that pump's water, so they had their servants go there and take the water from there. Other people are like, really, this seems closer to these people, but actually it was easier to get to that one just because it was a busy street or something. Like, it all eventually turned out to come down to that pump, all right? And so that's a fun idea, all right? So that map caused Jon Snow to think, all right, maybe it was the water after all. And so he devised an experiment. Some more backstory on this is there were a couple different companies supplying water to London. I think it was this one, Southwark and Vauxhall. they were supplying water to like the green. Sorry, this is a horrible image. Like the green bits of London. There was another company called Lambeth that was supplying water to a different part of London, but there was some overlap. There was some overlap on the companies. All right. Some of them supplied pumps. Like they each had some pumps in this area together. That's something that's important. So there's that, and it ended up being Southwark and Vauxhall. Their pump was the problem. All right, there was an issue with their water and where they were getting it from. I think what kind of went on was like, I don't actually know where the river is. I assume it's kind of right here, probably. Here's the River Thames. There it is. And as the water's flowing, I think what happened was like the Lambeth company, where everybody was fine, they were getting their water from like up here before the city. And then Southwark and Vauxhall, they were probably like getting their water from down here after the city started. And what happens to rivers in cities, I think you can imagine, is people like they're pouring their waste into that. And so if you get water after the stuff has been poured in, you're going to get sick. So that's kind of what happened. And so Jon Snow, he saw this map, he made this map. He's starting to think it must have been the water. So he's trying to make an experiment to prove causality. He wants to know for sure, was it the water supply that was the issue here, causing the cholera? And so he made an experiment. Right, here was his experiment. You're going to see these words that we talked about all over again. Here's what was going on. He couldn't really tell people to like, you go drink this water. Everybody was going to go to their closest pump, of course. But what he did was he formulated it this way. There is going to be a treatment group and a control group. All right. So the treatment group are the people like getting the treatment, the people who are getting usually more cholera. That was the Southwark and Vauxhall Company water drinkers. That was going to be his treatment group. Those were the ones he was going to study closely to see like, was there anything special about them? Why they were getting cholera more often? Control group, if you haven't heard that before, that's another common term in like studies that are done on like drugs, but it's still true here. Like the control group is just the person who doesn't get the drug. It's the people who did not get the treatment. And so that's the other company, the Lambeth water drinkers. All right. And what he did, the ingenious thing that Jon Snow did is he studied the people right here where the two companies met. So there was no difference between the people living there other than the water that they drank. That's what he figured out. All right. If you can get rid of any other possible difference between people, like whether they're rich or poor, stuff like that, then the only thing left is the truth. All right. So this is what he discovered. This is a quote from his study. There is no difference whatever in the houses or the people receiving the supply of the two water companies where they overlapped. It's like they were just as rich as each other. There's nothing else that could have caused one person to get more sick than another person, or in any of the physical conditions with which they are surrounded. They're all living in the same amount of filth, because London back then was a little bit dirty. There was no difference in all the people right here other than the water that they were drinking. That's what he concluded. And once you've whittled everything else down, you can prove causality. That's what he did. All right. So the two groups were similar. There were just as many rich people drinking Southwark and Vauxhall water as people drinking Lambeth water, stuff like that. The two groups were similar except for the treatment. If you can show that that is true, you can prove causality. If the treatment and the control groups are similar apart from the treatment, then the differences between the outcomes, right, whether they got cholera or didn't get cholera, can be ascribed to the treatment. That is how you do a good experiment. If you can get rid of, if you can randomize, usually we randomize things so that like just as many rich people, just as many healthy people are in this group, just as many rich and healthy people are in this group. That's a thing. If you can do that and show that there's no difference, like people are accounted for in both groups, the same kinds of people, there's no real difference between them, other than the treatment, which is the water consumption, then you can prove causality. Does that kind of make sense? If you can whittle away all the other factors, you're good. All right. And that's what he showed. So here's the data that he took. We've got the Southwark and Vauxhall Company. What do they got? They were supplying water to this many houses, people using pumps from that many houses. I'll go into the nearest one. It had to be from them. There were this many cholera deaths per that many people. And if you do like a division to get like a similar number, there was 315 people getting cholera and dying from it per 10,000 houses. All right, for Southwark and Vauxhall. For Lambeth, for their company, they were supplying not as much water to as many people. They had fewer pumps, I guess. They also had, because they had fewer pumps, they had fewer cholera deaths. But again, if you do the rate, what was the rate? It was much lower. Only 37 people dying from cholera per 10,000 houses for their company. And then there was a completely different company, because all these people are on the south side of the river. The north side probably had a different supplier. In the rest of London, there are a lot more houses still. There's a whole other side of the river to talk about. They had that many deaths, but again, if you take the rate, it was still much smaller. And so he saw that, all right, there's nothing different about these people, especially where what's the word? Where the companies overlap, the area that they service, their service area. That's the word I'm looking for. There's nothing different other than which water company they were using. And so he saw that the Southwark and Vauxhall water drinkers were getting sick much more often, and that was the only difference between the people in those areas. Therefore, he concluded it must have been the water. It must have been the water, and they were able to eradicate it, kind of. And so that's kind of the father of statistics and data science. That's a fun story. I think that's cool. All right. So you have to be very careful when you're doing these kinds of experiments, but this was a good one, all right? So you do have to be careful, because sometimes when you have treatment and control groups, they do have differences between the people in those groups, like the water drinkers, the non-water drinkers, the chocolate consumers, the non-chocolate consumers. Like I said, there might be wealth differences, stuff like that. They might have systematic differences other than the treatment. Then that makes it really hard to identify causality, because it could have been one of those systematic differences, right? It could have been wealth, it could have been health, stuff like that. So yeah, that's very common in observational studies. You do have to be very careful when it's an observational study. You're asking somebody, what did you eat chocolate? You're not forcing anybody to do something. Because you can get a better outcome. It's easier to prove stuff if you force people to do stuff. You're getting the drug, you're getting the placebo. Let's see what happens. That's much easier to identify causality at that point, because you've kind of averaged away the differences of those groups at that point. So yeah, you do have to be careful when it's an observational study, but sometimes when you do an observational study and you don't notice the systematic difference when you publish, those things that were leading you astray are called confounding factors, all right? So the moral of this story, you probably heard this phrase before, is correlation is not the same as causation. Correlation. You have to show very carefully that, okay, you found a correlation, you saw an association. Did that really lead to causation? Does that really imply that it was the chocolate? It was the water company? In one case, yes. In another case, no. So that's fun. Any questions about that? Does that kind of make sense? So when you're going to be a data scientist, we're going to talk about randomized controlled trials, and that's what you want to do. All right. So just some fun examples of this idea of correlation is not the same as causation. Here are some funny graphs from the internet. There's a whole website dedicated to this, actually, where people find weird correlations and they have obviously nothing to do with reality. So here's a fun one. We've got on the left side of the graph, per capita cheese consumption over time. So time is on the x-axis. Cheese consumption. People love to eat cheese, apparently. They like to eat cheese more often as the time goes on, apparently. And then we've got on the other side, this axis, this y-axis is now people who died by becoming tangled in their bed sheets, which is apparently a thing. Unfortunate. But you see how as cheese consumption increases, so does deaths by bed sheets. Does that mean we should outlaw cheese? Confounding factors, yes. That's the thing. It could honestly just be population, more likely. So that's something like that. Okay, so that's weird and doesn't make any sense. So there's also, here's another one, more dairy adjacent products. We've got per capita consumption of margarine, again, over time. So people are consuming margarine. It used to be very popular, and health conscious people would not eat actual butter over time. So that went down, which is nice. Butter for the win. And then we've got on the other side, divorce rate in Maine. So it looks like as fewer people are eating margarine, fewer people are getting divorced in Maine. Does that mean we should outlaw margarine? Save everyone's marriage? Probably not, right? Again, there's something else at play. All right, confounding factors. This was just if you look for enough, if you draw enough graphs, you can find the same shape with another completely random picture. Okay, so that's the idea. Correlation is not causation. The one thing I want you to take away from today. Yeah. Okay. One way to solve the problem, as I've tried to hint at, is if you use randomness. You flip coins. You're like, all right, if it's heads, you're going to get the drug. If it's tails, you're going to get the placebo, but you're not going to know. You're going to pretend you got the drug, or nobody's going to know. If you assign individuals to treatment and control, those two different groups, the people who got the drug, the people who ate the chocolate, the people who drank the water, and the people who didn't, controls, the people who didn't get the treatment. If you do that at random, then the two groups that you've created, you've averaged away all the differences between those people. Does that kind of make sense? You put just as many rich people, just as many poor people in this group, just as many rich people and poor people, healthy people, unhealthy people in this other group. You see how that randomness is going to average away any possible difference usually? That's what you want. And that's why you can prove causation from it, right? So with that, you can prove using some fun math that any variability, like you can get rid of any other variability because sometimes you can't like have exactly the same numbers of people in each of the groups. Like you can't manufacture as many of the drugs, for example, like there's a bigger control group or something, but you can always account for the variability once you do it this way. You can make sure like once this happens, like you've made these two groups, you've averaged away any possible bias. That's another word. So there's no bias anymore. Usually, all right? So that's what happens. Any other variability you can account for. And this is called, when you do it this way, it's called a randomized controlled experiment. You've set up the groups randomly. Because of the randomness, any possible confounding factors, right? Any possible confounding factors will have been accounted for and averaged away, usually. Okay? And so you can draw causality conclusions from a randomized controlled experiment. That's ironclad, that's gold standard, that's how people do things these days. Okay? Does that make enough sense? And when I say random, I do mean like they're kind of flipping a coin, but randomness we love in this class. Randomness is going to be the backbone of how we like run experiments and tell the computer to do it for us. Random has another definition in English, right? It has the definition of like you're doing something just random, carefree, haphazardly, where there's a negative connotation to the word. That's not the kind of randomness we're talking about in this class. We love randomness. Randomness is just like complete randomness, like you're flipping a coin, you're assigning people to groups. It's not careless. It's not haphazard. It is averaging away any biases. It's a good thing for us. Okay? So we love randomness in this class. We're not using that connotation. So yeah, here is an example, a great example of a randomized controlled experiment. This was the Pfizer COVID shots. They did a randomized controlled experiment. They had a treatment group, the people who actually got the shots, and they had a control group, the people who did not get the shots, but I mean, they got something. It was a placebo. They didn't know if they got it or not. And so the people got the second shot on day 21. Here's like days after they got their first dose of the Pfizer COVID vaccine. I think that's the one I got. And then here is the rate of getting COVID. The red squares are the people in the trial who did not get the shot. They got the placebo. And then the blue circles are the people who got the Pfizer shots, and this is the rate of them getting COVID. All right, so these were random groups, which means the treatment and control groups, any differences between those people was averaged away. And so you can see that after the second shot, like they were getting COVID at the same rate for a while, but the second they got the second shot, you can kind of see how this one plateaued. There are still some people getting COVID who got both shots. Like that's just going to happen. But everybody else, the people who did not get that second Pfizer shot, they didn't actually get the real vaccine, their rate of COVID just kept increasing. And so you can conclude from this graph that this shot worked, and then you give it to everybody. That was their trial. Does that kind of make sense? You can prove once and for all that like the Pfizer vaccine really, it caused a lower COVID outbreak. So it helps people. So yeah, I think that's what I wanted to say with that. That's how people are doing things these days. That's how you can prove like, okay, yes, give it to the people now. It works. Yeah. I hope that makes enough sense. The last thing of these slides I want to show you while you think about any questions that you might have is here's a fun comic that you can now laugh at if you couldn't before. So ponder that while I get ready for the next set of slides. And yeah, do you have any questions about like these experiments, these words that we've been throwing around? Are some of them familiar to you? Just shout out, just yell at me. Yeah, if we're good, I would like to talk about Python some more. Would we like to go there? Are you ready for that? All right. Let's do it. All right. So here, I need to make a new Jupyter page for today, but this is going to be on chapter 3. So we want to read chapter 3. I'll talk about that more in a second, but I want to teach you the basics of Python today. Like we learned how to do math last time, but that wasn't really the full story, of course. And I showed you a bunch of stuff, but I did not expect you to understand it. Now we're going to go slowly, and I'm going to show you things that you can understand, okay? So I do want to say at the start, like the mascot of the Python is programming language, right? The mascot of the Python programming language is a little snake. It's really cute if you go to their website. But actually, the name Python, the programming language Python, was named after the Monty Python comedy group, if you heard of them. So you'll find a lot of references to them just as jokes in their documentation pages. So it wasn't actually named after a snake. So it was named after them, which is funny. And yeah, I'm going to teach you some Python now. This is chapter 3 stuff, a bunch of fun things you'll learn today. And please start reading chapter 3. These are all short chapters, 1, 2, and 3. So you should get through them quickly. But make sure to be reading those chapters because there's going to be things mentioned there that I didn't mention. And you got to get both. All right? It's good to hear the same thing twice, too. So yeah, let me make a new file. Let me show you some Python. Dun, dun, dun. If you want to follow along, remember that you can, if you brought your laptop, of course, you can make your own page in the Jupyter Lab desktop program. But also, you can always go to, please remember to do that attendance too. I'll stop that eventually. Remember, you can always also go to this Jupyter Lab page at the very bottom. There's that link for like a temporary Jupyter Lab tab. You can always follow along there if you don't want to install something on like the big computers. Okay? So yeah, one of those places, I'd encourage you to follow along. I'll ask you some questions soon anyway. But let me make a new folder, or not a new folder, but a new file for chapter 3. That's how I'm going to name all these files. This is called chapter 3, and so I'll give that to you after class, just like I gave you chapter 1 after class on Monday. Yeah, let's do it. So here is a cell in Jupyter. And you can put any Python code you want there. So we know from before, right, that we can do just like basic math with Python, like 2 plus 2 is Python, technically. And so you say 2 plus 2, that's my cell. With the code in it, you can press the play button to have that run and show you the output of the last line. It's always the last line, right? There's that one. We've got, remember that if you want to do something quickly, there's for star 2 is times. Star is times. If you want to do something quickly, like you want to move on as fast as possible, you want to move your hand to the mouse, it's shift and enter at the same time to have it run the cell and produce the output and make a new one for you. So I'm going to press shift enter instead of the play button, and it does that. So that's a little bit quicker. Okay, so there's that one. We know that that's multiplication is the star. We've got, we learned last time as well that the double star is to the power of, so 4 squared is 16. There's that. I next want to show you errors, because maybe you noticed this if you type something wrong, but I was very careful last time to not make any mistakes in Python. But it's totally possible to speak Python incorrectly and to have it be like, I have no clue what you're talking about, dude, and it shows you an error message. So let me normalize that, because that's going to be our life in this class. Everybody makes mistakes. And so this double star, this like to the power of operation, actually needs to be together. You can't put spaces. Like you can do it 4 star star 2 without any spaces around that. But if you put a space after one of the stars, now it thinks you're trying to say multiplication twice. And so if I press shift enter, or if I press play now, it's going to give me an error message. It's going to say invalid syntax. That's going to try to put, like, it's got the little caret there pointing to that second star, being like, I was not expecting that second star. Can you kind of read how it's saying that? So it's usually pointing to the problem. Sometimes it points to something else that kind of was a result of the real problem, but you'll get, the more errors you make, you'll get better at figuring out what was the issue. Okay, so those are errors. There are plenty more where those came from. We all are going to make mistakes. You'll see me have a bunch of error messages and try to fix them, but that's just a fact of life in Python. It's gonna spit out error messages at you sometimes. Do not be afraid. It'll be okay. Okay. The next thing I want to say, and please just shout out if you have any questions about this stuff. The next thing I want to talk about is called a comment. So usually when you're writing code, it's not just all Python code. You want to leave yourself like a little sticky note for next time when you come back and you open up the program a week later, the notebook a week later, and you're like, what was I doing here? If you want to leave yourself little notes, you can use what are called comments in your code. All right. So a comment is the ones that I want to teach you at least right now. Comments are lines that have a number sign in them. So a number sign, the second you write one, it can be on normal code lines. This begins a comment. It's called a comment. It's a little sticky note for yourself as the programmer. It's not real code. It doesn't get run. The second you say a number sign from there to the end of the line, that is just a note for you or for your peers or for your coworkers or whoever's going to see this code later. So this is called a comment. You see that it's colored in differently as well. This is a comment. It's just a note for the programmer. All right, so it's not actually code. If I run this cell, nothing will happen because I didn't have any real code in it. So you can say whatever you want right here. All right, it's a comment. It's just for you. All right, it's not code. You can put other things underneath it. You can be like 2 + 2. And you can also put comments after code, and that it just begins the comment there. So like I can leave a note for what this line did if I forgot, right? This adds 2 and 2, right? The only real code in this line is this part. You see that? That's the only real code. Everything else is just a little sticky note for me to remind myself for later. If I press Shift Enter, if I run this cell, it's going to run the only piece that was the real code. See that? So that's useful and necessary. All right. So next, are we ready for variables? I said those names back on Monday, but I want to actually introduce them from scratch now. Okay. So a variable is just a name for some intermediate, like some computation that you want to save for later, so you don't have to like say the words of the computation all over again. So the way that you make a variable is you say its name, like I want to make a variable called x, for example. Is this in the right folder? Yeah. I want to make a variable called x, for example, and I want to have it hold something for me for later, and I want to be able to say x instead of whatever the long thing was. So I want to have x maybe hold a number, 42. So the way that you have that happen in Python is you say a line that looks like this. This is called an assignment statement. You say x equals, and then what you want to have the x variable hold for you. And so it's a little bit different to the mathematical equals. It just kind of like sets 42 into x. That's how I want you to think about it. Okay. So that has created kind of like a little box in the memory of the program, and it's holding on to the value 42 at that point. And now if you ever say x, once you've said this line, if you ever say x, like x times 2 or something, it will get at that 42, whatever was living in that box at the time. That's useful. It's shorthand for long things. You can imagine that that's going to be useful for us. Okay. So, for example, a good thing that you could do, this is part of a library that we'll talk about later, but you can be like, I would like to make pi, so I can just say pi, pi, instead of like 3.14159.265, so 27, right? That's the thing. And now I can just say pi all day long rather than having to remember what actually pi was. See how that's shorthand now? That's useful. So if I run this cell, no output appears. It just set up the box. There's a box now called pi that holds on to that value. If I ever ask for it later, I can be like, pi, what are you? And it outputs whatever it thinks it has. That's what was in the box. So this is now linked to that. Does that make sense? What a variable is doing for us. It's holding on to a value, and you can use it in a bigger context now. I can be like pi r squared, pi times 5 squared if I was the radius. There was the area. Right? See how easy that becomes now? It's a lot easier and cleaner to read, like what you were doing here. Oh yeah, you were using pi. Yeah, that was quick. That's nice. So that's the thing. So you can do the same thing with other variables. You'd be like x equals 5 or something, like save the number 5 in a variable called x. And so now if I ever ask for x, it's really holding on to 5. It's the box holding 5 in memory, you can imagine. And you can use it in a bigger context, like what's x times 2? You can do other math with it. Usually that's what you're going to want to do. And that's how it works. Okay. I do want to say before I move on, Yeah, I'll show you an example of this in a second, but the way that this works is oftentimes you're going to have something that's not just like a number on the right side of that assignment statement. You're going to have something that becomes like a number sometimes. So like you got your variable name, and then maybe you'll be like, I want my variable to hold this result, like 2 plus 2. Can you kind of imagine what you might want to do that one day? Like do the math and then put the answer in here. That's kind of what you're saying at that point. So when you say something like this, it's not going to put 2 plus 2 in the var box. It's going to put 4 in the var box. It's going to do the math first. All right. So every time you write something that needs work to be done, it's called an expression in Python. So like 2 plus 2 is technically called an expression because it's work yet to be done. You can still get an answer from it. So an expression is something you can get an answer for eventually. It's not ready. An expression, we say, evaluates to some final answer that cannot be simplified anymore. And that final answer is called a value. All right. So there's like an evaluation process on 2 plus 2 that we evaluate it. Python evaluates it to 4. And then it's the 4 that's going to be shoved into the variable. All right. That's what's going to happen. And that's going in there. Does that kind of make sense what's going to happen there? That's what Python is going to do for you, okay? That's lovely. Does what you would expect, all right? So it does the math, once and for all, shoves the answer, the final value of an answer. 4 can't be simplified anymore, but 2 plus 2 can still be simplified. It's just an expression. It shoves it into the variable that you gave it a name for, okay? So let me now make you feel uneasy. So I said x equals 5. The reason I want you to not interpret this as like mathematical equality is because I can come along later and be like, you know what, x? You're holding 42 now. You can do that. Python doesn't care. That's a thing. So this is going to overwrite. Overwrite. See the use of comments? Overwrites the value of x. All right. So even though you said it was 5 before, now it's going to be 42 once I run this cell. See that? That's going to happen. You can do a bunch of things. You can have more lines, more than just one line per cell, and Python will run each of those lines in order, each of those thoughts. Right? I can be like, all right, let's make another variable called y. Let's have it hold 43. And the real answer that I want is the result of x plus y. Does that kind of make sense what I want this cell to do? Define x to hold 42, whatever it held before, who cares? It's 42 now. Make a y now that holds 43, and I want this answer of x plus y, because that's what's going to be evaluated, and it's the last line's answer that gets spat back out to you. So that's 85. And that was very easy to see what I did, right? You can come back later, read this program very easily rather than saying 42 plus 43. A lot of the time, like the longer you can make it, the more wordy you are, the easier it is to understand. So does everybody understand what this cell is doing, how I made that answer? All right. Another very weird thing, this will make you feel even more uneasy if you haven't seen this before. I can do this. I can say x equals x plus 1. And then if I say x, I can have it print out whatever it thinks x is going to be now. What do you think it'll print when I run this cell? You think it'll be an error? What do you think it should show? Thoughts? Well, maybe my first question is, before this cell gets run, what is x if I ask for it?
42.
It's 42 right now, all right? What should happen then? What should I see? Yeah, this is really weird. We're going to see 43, all right? Can you kind of understand why? What's happening is this picture all over again. You're always making an assignment statement, and sometimes you're putting stuff, right? That's an expression, something that needs to be evaluated to a final answer still. Python always runs the right-hand side first, so there's no ambiguity, all right? Python always runs the right-hand side first, oops. Therefore, because of that, so right-hand side, RHS, right-hand side always gets evaluated, and then put into the left-hand side, which was the variable's name. So this is always going to be the order. So Python right now, x was holding 42. It's going to do this math first and compute 43, because x plus 1 right now is 43. And then it will shove the final answer of 43 back into x. You see what's going on there? That's what's going to happen. Okay? Any questions about that? That's a weird one. That's something you'll get used to. It's a useful thing that we're able to do that. But I'm sorry they called it equals sign. Honestly, they should have called it like arrow or something. That would have made more sense. Some languages do it that way, but we've all gotten used to the equal sign. It's one less thing to type. So yeah, here is a reason you would want to use variables if it's not clear to you yet. Like, let's say, no, yeah, I'll do it with you. There's that. Something like this, like you're making a program to do your taxes or to compute the final answer for like the price you're going to pay at a register or something. So like the subtotal of the thing you're about to buy before tax is like $9.99, and so like put that into a variable to make it obvious what's happening. And then like the tax based on the subtotal is like, how do you calculate tax? It's whatever the subtotal was, right, times whatever the tax percentage is for the county and the city or whatever. I honestly don't remember what it is for Fresno. I think it was 8.75%, so it's times 0.0875 for like Fresno's tax. And then the final answer that we want is what's the real price that you're going to pay now. That's the subtotal plus the tax. You could have done this on one line just by saying like $9.99 plus 99 times 0.0875. But do you see how much cleaner this becomes now? You can see exactly what's happening when you do it this way. When you name it all, you can come back in a week and understand exactly what was happening. Whereas if you did this on all one line, you have no clue what kind of thing you're actually computing. This makes it clear. That's apparently how much you're going to pay once you round it up to the nearest cent, or nearest 5 cents now that we're getting rid of the penny, right? Crazy. So yeah, that's kind of the basics of variables, assignment statements, and like math and stuff. Comments as well. Are there any questions about any of that before I move on? Not too horrible, right? Let's see here. How do I want to do this? All right, let's talk about using other people's code now, because we're using the star and the plus. Those are built into Python. That's technically other people's code running when we do that, but there's more to it, of course. So I want to talk about what's called a function call. Your book is going to call these things call expressions. That's like the Python name for it. But in general, for a programming language, what we're about to do is call things called functions. Okay, so a function is pre-written code that some nice smart person somewhere else made for us. I'll eventually teach you how to make your own functions, though. That'd be great. And what you do is you're kind of shouting to it, like that's the metaphor. Like you've got a function, which is somebody's pre-written code. You're yelling at it. You're calling over to it. Hey, please do this work for me, and it gives you the answer back. Okay, so when you call a function, you're asking some pre-written code to go off and do something for you. The way is to say it's called a call expression. And here's what it looks like. You say the name of the function that you want to call when you ask it to do some work for you. And then in between parentheses, you put what are called arguments of the function. All right, and you separate them with commas if there's a bunch of them. So these are called the arguments of the function. They're whatever the function needs to do its work. Like go and do this math, like here's the subtotal, here's the tax rate. Like that's something that one of your functions might need or something. It needs everything. You give it all at once between commas, and those are called arguments to the function. Like again, using the metaphor of like you're shouting at it, you're arguing with it, you're calling to it. Okay, so here's like a simple example. Like if you have a function called f and it takes one argument, you can give it in this way. You say f parentheses and 42 was the one argument that it was expecting and that it needed to do its work with. All right. So that's you kind of shouting to the function, hey, f, go and do what you're trying to do with 42. 42 is the thing you wanted. You wanted one thing. Here it is. It was 42. Give me the answer back with 42 as the input. Okay. A good example of a function that's built into Python is the maximum function. It's called max. And you give it as many arguments as you want, actually, but 2 is the usual amount. And the max function is going to give you back the maximum of the arguments that you gave to it. That's a useful thing, right? So you say max 2, 3, for example, and this will call to max and say, hey, I want you to find the max for me of 2 and 3. You kind of see how that one is meant to be used. They're all meant to be used in different ways, but like that's what maximum does. So this calls max with 2 and 3, and it's going to give back its answer. Another way of saying that is like it results in its answer, it returns its answer. You'll hear me say those words. It's going to give back the maximum of 2 and 3. It's going to do the work for us. It's going to give back 3. This entire call expression will be turned into 3. Does that kind of make sense? Like somebody's going to do the math and do the work for us, figure out the bigger thing. They'll give me back the biggest thing, the maximum. Okay? And it'll work for whatever numbers you give it. That's the whole point of having functions. You can call it with in a bunch of different ways, a million different times, and it will always be there for you. Okay? So yeah. So let me make a new little section for us for function stuff. I'll say function calls and make it nice. Function calls. Make it nice and big. So that's a fun thing. I can make a little section. So instead of a code cell, what I did there was I made something called a markdown cell, if you care about learning this. This is called markdown. So I actually made a number sign there in markdown. The language makes a header, which is kind of cool. It's not a comment. So this is called markdown. It's a programming language for like making pretty text. You can think of it as a programming language, but I'll say that between quotes. To make pretty documents. You don't have to learn it in this class, but like Discord uses Markdown if you want to make a fancy Discord message. It's worth learning. So yeah, we got the maximum function. Max23 gives me back 3. You better believe that it works no matter how you call it. Like 5, 4, -2. Gonna give back 5. It's like, give me your arguments, I'll give you back the maximum thing in them. Does that kind of make sense how you use that one? So I'll go back to the original. 2, 3 resulted in 3. Okay, so it results in 3, and it gives back its answer. What else do I want to say? Yeah, let me use some more of them really quick, and then I'll show you some things. All right, I think that's what I want to do. Yeah, that's the order that I want. There are other functions that you could be using, and I want to show you that these like result in things. So what we might have wanted here, we had subtotals plus tags. And you can't have 1,000th of a cent, right? You can't have any more than that. So we really wanted this to kind of be rounded down to 10.86. There's a function for that. I could have said, instead of just subtotal plus tax, like give that to, there's a function called round. Makes sense? You say round what you want to have rounded. It can be an expression still, like it'll find the final answer. It'll round its answer, round the value, to 2 decimal places. So round takes 2 arguments always. The thing you want to round, I guess also you can omit the 2 if you want it to just be rounded to the nearest whole number. But usually you give it 2 arguments. You give it the thing you want to round, which can be something that needs to finally be evaluated. And then you give it how many decimal places you want it rounded to. And so that creates 1086 for us, and that's what you kind of show on the checkout stand. That's useful, right? It's a function. It's pre-written code that somebody made. They worked very hard on it to like round that one down and other ones up. Okay. Does that make sense? Calling functions. You're asking it to do something for you. All right. There's also the absolute value function, which is a good one. Absolute value is called abs. It's built into Python, and you just give it the one thing that you want to take the absolute value of. So like -42 will result in +42. If it's already positive or 0, it's going to stay what it was, but it'll chop off any negative signs. That's what the absolute value function does. Okay? Any questions about me calling those functions? You kind of see how they're going to work? You can imagine there's also a min function. Does the minimum. All right. Here's my question for you now. I would like you to play around, and the best way for you to learn this stuff is to not try it in Jupyter. Like for a second, please do not try this. But if you want to write down your answer, you can. Here, humor me. I'm going to stop attendance after this question, so please do attendance if you've not. But I've made a nice little page for us called Written Ice, written in class exercise. And you can elect to, I would like you guys to now get into little peer instruction groups. Say hello to the people sitting next to you. Introduce yourself if you haven't met before. But I'd like you guys to please work on this question. Try to do it in your head. What will be the output of a cell with this line of Python code in it? Give me the max of the minimum of that, the max of that, the minimum of that, plus 42. Can you follow the parentheses and follow the function calls and the chain of them? Try to do it in your head. You can, of course, check your answer, but try not to until you've gotten the final answer yourself. And if you'd like, so that we can see if we all agree, you can go to this Written Ice page and you can enter in your answer, the one that you come up with. So please say hello to each other and try to convince your neighbors that you're right. So give that a try. On paper first, or in person. Before you check it on Jupyter Lab land. And enter in that answer once you've got an idea of it. So my hint is that outer max, it can't do its work, right? It can't do its work until it knows what the inner things are. So it's going to run those first, won't it? All right, was that enough time? Are you still thinking about it? Let's see. I guess you can check your answer, but still, it's worth figuring out. And any questions come up as we thought about this that I can help answer? Because there's more to it, right, than just showing you what's happening. You kind of want to understand what's going on in Python land as it's trying to execute this code, right? So let's see. Yeah, looks like all of us got 48. Nice. I think that's the right answer. Very good. Very nice. All right. I promise I'd stop that. Cool. Thank you. Thank you for that, getting your answers in. Let's try to walk through why it's going to be 48 now. So max, if you can kind of follow the parentheses, it's this big guy plus 42, right? So you got to do that one first. And so max, we're trying to take the max of how many things? It's 1, 2, 3 things, really, right? See how they kind of like, you got the inner bits now? And so max needs to find the maximum of whatever of these is the biggest. And it's not sure yet, right? So what Python will do is the logical thing. It will go and it will run each of those inner calls, those inner arguments to the outer max and get their answer so they can find something concrete to get the max of, right? So the min of 1, 2, 3 will give back 1. That's the smallest thing, right? The max of 4 and 5 will give back 5. That's the biggest thing. The min of 6 and 7 is 6. That's the smallest thing. So now max sees, this kind of turns into, right? This call now turns into essentially this. Like this whole code turns into now max 1, 5, 6 plus 42. That's what's going on in Python's head. It did that first. Does that make sense? That's what's going to happen. All right. And so now you can clearly see what max is going to give back. It's like, all right, that's going to result in 6 now. All right. So max is going to give back 6. That's what it returns. And so all this code now turns into 6 plus 42. Do you see like the stages of how Python's running this code? It's logical. It's how you would expect it to. And then the final answer is 6 plus 42. It computes that final thing. It evaluates that final smallest expression to a value of 48, a whole number. Okay? Lovely. And that's why we give it back as 48. Does that make enough sense? See the progression of that? Yeah, please shout out if you have any questions about that stuff. But that was a harder one. Good. So you can kind of see the magic of function calls. Now you can use them in inner function calls, right? It's going to find the answer eventually after it's done them all. It's lovely, all right? So with that, I have a couple more things to talk about. Today I want to talk about the concept of libraries. I think I threw that word around on Monday, but I want to tell you what that really means, and we're going to use some examples. So a library, again, I love the metaphors that they have in Python land. And across all programming languages. So a library is a bunch of pre-written codes, like functions, for example, that you can import. You can check them out of the code library. It's really cute. I like that metaphor a lot. So that you can run those things that are not just already built into Python. Some people have made specialized libraries, like there's one called the math library, for example, that gives us access to functions that some other smart people have made just for math purposes. And so by default, it's not available to us yet, but we can check out that code for us to use for our programs. Okay. So you can imagine that the math library has like the sine, cosine, tangent functions defined in it. But right now in Python, if I ask for sine of something, it's not going to make sense. It doesn't work yet. I have to check out the library. It's called importing it. Okay. I have to import that library. And you can check out what all the different libraries are in Python. Like there's a math library. You can see what's in it by saying, like, you just search Google for like Python math. And the first one is the documentation for the math library. So if you import this library, this is what it gives you. All these things. Greatest common divisor, some fun things that are hard to explain. E to a power of something. You've got inverse sine cosine tangent and normal sine cosine tangent. And you've got a constant. You've got the actual pi defined, like as long as it could do it with the most precision. You've got the constant e. You got fun stuff like that. All right, so that's what this library gives us. If we check out this library, if we import this math library, we get access to all these functions that we don't have already in Python. We can get them for free though, all right? So another good one is the square root. Where was that? Did I pass it? The square root of a number. Here's another way to do powers. Power of the first thing to the second thing. So square root is a function. You can always click on these to see more about it. Like square root of something, it just gives you back, as you would expect, the square root of that one thing. It took one argument, the thing you wanted the square root of, right? So that's what happens when you use a library. You're checking out some code that some people put in a special place that's not already available for us. So for example, the square root function doesn't already exist in Python. It's not built in, but we can import it from the library. Okay, so libraries. Let's make a little section for that. And so, like I said, if you say square root of 2, it doesn't exist yet. It's like square root is not defined, but it's part of the math library. If I check it out, if I say that I'm using it, then we can have it, okay? So what you do if you want to use the math library is you say import, and then the name of the library you want to import. We say import math. That's just on a line by itself. And then from then on, once you run this cell with this in it, you have access to the math library stuff. Some of the things are functions. Some of the things are variables. Like there was all these things down at the bottom. Where were they? Right here. These are variables defined in the math library. So math defines the variable pi for us. So we can use that, and we don't have to remember it ourselves. So that's nice. And it also has the functions, of course. So once you import a library, you still just can't say square root, because it's possible that there's like 2 math libraries that you're importing and it's ambiguous which square root you wanted. So this still doesn't work. The way that you get out a library's function is you have to prefix it with the name of the library and a dot. So you have to say, I want to use the square root function from the math library, please. You say math dot square root. Because it came from the math library, we're prefixing it with that, just in case there was another library that also gave you a square root function. That's how you keep it from being ambiguous. That's how Python does it. And so now you get it. So it's going to be math.square root, math.sine, math.pi. All those things exist. Okay? Does that make enough sense? That's how we're importing that library. Now we have access to those functions that were defined for us. Those are useful ones. All right? If you have any questions about a function that you're trying to use, you can, of course, go to this documentation page, but a faster way, a cool way in Jupyterland is you can type the name of a function and then put a question mark. So like there is a logarithm function that I think, was it natural log probably? Where are you? Yeah, here's a logarithm function that takes 2 numbers. By default, it gives you the natural logarithm, but you can also say base whatever you want. So like base 2 or something, base 10. That's math.log. If you had a question about that and you didn't want to go to the documentation page, because we're lazy as computer scientists, as data scientists, as whatever we are, you say math dot, the name of the function that you want to try from the math library that you're not really sure about. You just put a question mark and you run that cell. And it gives you back the documentation on it. Isn't that cute? That's nice. So if you forget, just like run it with a question mark real quick, and it tells you about it. It's like, okay, yes, log takes at least one thing. By default, the second thing, if we didn't give it, it's going to give base e, natural logarithm, but it could also be base whatever we want. All right, so that's how you do it. Yeah, and then you can go and you can use it, of course. You'd be like math dot log of 32 base 2. So this is the base 2 logarithm 32, 2, 4, 8, 16, 32. That's 5 is the answer. All right. So like, all right, I learned how to use it. Now I used it. Does that make sense? If you want, you can just say square root. You have to say it specially, though. There's a way to get square root so you don't have to put the math dot at the start of things. There's a way to get whatever you want out so you can just use it by its name. And here's the syntax for that. You import it from the library specially. So if I want to call it just square root, I say from math, import, and then you say whatever you want to import onto the top level, we say, without any dots. We say import square root. import sqrt. And the second you say that, for the rest of your program, you really can just say square root by itself. It's saying, all right, whenever you see square root, it's coming from the math library. So now I really can just say square root by itself. It exists for everybody. You don't have to say math dot. So some people prefer to say it this way. Some people prefer to do this trick. It's up to you what you like. We'll use both kind of interchangeably in the class for some special libraries that we use. But yeah, I think that's what I wanted to see or say there. Are there any questions about, for example, the math library? There are more, and you can look into them. And I'll talk about some later, but that's a good start. So when you use a library, you have to import it. Then you get access to its stuff. All right, we're almost to the end. Now this next slide will take a while. The next couple slides will take a second, but they're like the backbone of this entire class, kind of. So if we're ready, the last thing I want to say is, oh, why is that open? The last thing I want to say is I want to talk about tables, because we talked about those on Monday. They're going to be the backbone of data science in this class. It's got like a two-dimensional grid of data. That is a table for us. And they live in the data science library. That was a library made just for our class. Just for our class by the Berkeley people. But it's similar to libraries that people are really using in data science in real life. It's not too far away from them. Okay? You could easily learn them. So what a table is, it's a special kind of thing that you can make using the data science library. It's just a bunch of labeled columns is how I want you to think about it. It represents a grid of data, but each of those grids, each of the columns of those grids have names and labels, all right? So again, the metaphor is, this is a table. It's got 3 columns. It's got a name column, a code column, and an area, parenthesis, M2, parenthesis column, okay? So columns are like columns at the Parthenon, things that are going straight up and down, horizontal, right? Sorry, vertical, excuse me. And then from left to right, these are rows of data. These are just the labels, but this is a row of data. This is a row of data. Rows go horizontally. It's like you're rowing a boat and the boat is flat. Okay, so again, it took me a linear algebra class to get that straight in my mind. So don't worry if that's still hard to differentiate. But columns go vertical, rows go horizontal, and this is what a table would look like for us. All right, we're gonna be able to interact with these using our data science library. Okay, so it's a bunch of labeled columns. So there's a name column. It's got 2 things: California and Nevada. There's a code column. It's got California and Nevada as codes. It's got the area column. It's got whatever the area in meters squared of those states. Okay, and so yeah, these are labels. This is the contents of the column, really. But yeah. Data within a column, just like we'll read this and I'll explain it. Data within a column represents one attribute of the individuals. All right. So like this CA is the code part of this row, which is representing California. Does that make sense? That's how I want you to think of the table being broken down. This part of the column is one piece. That's the code attribute part. These are called attributes as well. One attribute of this entire row. Every row represents one idea. You would say individual, like whereas it doesn't have to be a person, it can be a state, for example. Okay. Do those terms make enough sense to us? Any questions about that? Because that's just, I'm going to throw those out for the rest of time. So yeah, that's what's going on. Once you make tables, then you can do stuff with them. It's great. All right, so let me show those to you. Tables live in the data science library, and we're going to import tables so that we don't have to say data science dot table all day long. We're going to import them in the way that I just did for square root. So tables. Boop. There we go. So here's how we're going to do it. All right, we're going to take tables out of the data science library in this way. We're going to say from data science. I could say import table, because the name of it is table with a capital T, but honestly, I just want to import everything in the data science library, whatever, like there's other things including table, separate from table as well, that we'll need. So I just want to import everything from the data science library so that I don't have to say data science dot. And the way that you do that is you say from the name of the library, import star. The star symbol just means everything. Import everything, so now I can just say table with a capital T and it's happy. All right, so the star imports everything into it's called the top level. I said that already, right? So I don't have to say like data science dot whatever. Dot blank. Whatever was in the data science library, I can just say its name. I don't have to say data science dot that thing anymore. I'm good. All right. So yeah, let me show you some table stuff. I'm very excited. So the way that you get stuff in, first of all, I got to run that. It takes a while because there's a lot of things, so thinking about it. But eventually, it will have it all imported for us to use. The first time you do it, it's long. That's okay. All right, it's ready. We have table, for example. And one of the ways to get a table into your notebook is there is a function on tables. It's a weird way to call it. It's like part of the idea of a table. It's table dot, so it's inside of a table now, rather than like inside of the math library. Inside of the table concept, there is a read table function. And you can read like a CSV file. And so that's what I'm going to do. But if you have any questions about any of these functions that I talk about, there is a documentation page, which I probably linked somewhere already, but I'll give you that link eventually in these slides. But you can also do the question mark. There's a really long documentation because this is meant for students. So table.readTable, what it takes is really just a file name. It also takes some other optional things that you don't need to do right now. But this is kind of how it works. You can also give it anything that could become like a CSV file. So even a website, it'll go there and it'll give it and make it for you. But I'll just give it the name of file eventually, not a website. But you could also use it for a website. So this is kind of how an example run of it. You like table.readTable. You give it like a website that gives you a CSV file, or like the path on your computer to a CSV file. Something that can result in that, and it will read it. It will read it for you, and it'll have it available for you as a table. Okay. So what I'm going to do is I've got the simplest table, simplest CSV file. It's called in my data folder in our code from class. It's called cones.csv. It's a little small. Sorry, I don't think I can make it any bigger, but I guess I can do this. Whee! It's for just a silly file that has a bunch of ice cream cones, imaginary ice cream cones. All right. So there's 7 rows of data, and there's 3 columns. The column labels are flavor and color and price. And so each of these rows are individuals, right? And they're like ice cream cones you could buy. So I want to import this table so I can do stuff to it programmatically in Python. So import the CSV file so I can do work on it. So it's called cones.csv. It's in my data folder. And it's always relative when you do it on your computer like this. Where I'm going to say table.read_table. And the one thing I'm going to give it is where that file is as a string, as something that has quotes, because it's text, as text. That's how I give it. Okay, that's what I'm going to do. As a string of letters. So yeah, the place it is. So I'm in this chapter 03 notebook file. Where the cones file is, it's in this data folder. So I got to go into the data folder first, / and then it's in the cones.csv file inside that data folder. And you can usually use the tab to have it autocomplete. And so once you say that, hit enter, shift enter, and then it's read it in, and now I get to use all of its data. See that? That's nice. What you want to do, because this is kind of ephemeral, it's gone now, I want to give this a name. I want to call this table something so I can reference it later. I'm going to use a variable. All right, so I'll call this cones, the variable. Shove that table, the whole idea of that table, into the cones variable, please. And so now when I print out cones, like I got that saved for later now. I can go to pieces of it. All right, does that make sense? So that's what I want. And now, are you ready to see some operations on tables once you got them inside of your code notebook? That's the last piece. All right. So let's see what I want to do. So here are your operations on tables. There's this file. There's some documentation pages. There's this link and this link. I can't remember if I've given those to you already. You'll get them once I give you these slides, of course. But I think they might be in this page. Yeah. If you go to the Jupyter Lab page, it's this reference 1 and reference 2 pages. Both of those will take you to these pages where you can find some more information on these functions in the data science library. And so here are things on tables. Like we just did table.readTable, but here's like an example again, just in a different way. There are other things that you can do to tables, like, hey, table, Give me how many rows are in you. That's the table's name .num rows. These are all things that you can do. That's one documentation page. Here's another one. It's a little bit more succinct. I'll let you use both of these on all of our exams in the class. All right. So yeah, like table.num rows, it tells you what it's doing, blah, blah, blah. All right, so you can look at either of those if you have questions, but you can also do that little question mark thing for a quick answer. Yeah, I've got this table called cones. I put it in the variable called cones as well, and it's got 3 columns and 7 rows, and I can play around with it. All right. So I guess the first thing I want to show you, the first thing that's not even listed here is you can do, there's a dot show on your table. So this idea of a dot is like you've got a table and you're asking it to do something for you. Like, hey, table called cones, do something. And so there's a dot show for your table. Let me show that to you. I'll just go to one of the documentation places. If you do dot show on a table, you can give it nothing or something. So it's supposed to display the first n rows of a table. If no n is provided, it displays all the rows. And this is how you're supposed to call it. So it's the name of the table with a dot and then show whatever. All right. So if I got my cones table here, if I say cones.show2, what that will do is it will show the first 2 rows of the cones table. And sometimes that's just enough. That's all we needed. If you give nothing to dot show, no n is provided, displays all the rows. For us, it already displays all the rows, but for longer tables, it only displays the first 10 rows by default. If you say dot show, it'll show every single row, even if there's a million of them. So that's useful as well. So that's dot show, and you can go to any of these and look more into them. Okay. The next one I want to show you is dot select. So if you have a table, let's pretend it's called T. You say that table's name dot select, and then you can give as many arguments as you want, at least one, that will give you back, that's names of labels you want to pick out of that table. And it will make a table with just those labels only, forgetting any others that used to be in the table. Okay? That's what dot select does. Again, on the documentation page, you can see that somewhere. Dot select takes a bunch of labels for columns. And so if you had a longer table, you can select out just the ones you want. Or if you give the original ones, like all of them, in a different order, it will rearrange them. That's also useful. Okay? So that's the thing. So I'll say that. So I have my cones table. If I say cones.select, I can start giving names of columns. And the names of my columns are these labels right here, flavor, color, and price. And I give them between quotes because they're text. That's how you give labels like that in Python. So I say quotes flavor. If I just want a table consisting of only the flavor column right now, I just want to see all the flavors that we offer. If I run this cell, Shift Enter or the play, it gives me back another table, but it's really just the row, or sorry, just the column, excuse me. It's just one table with only the flavor column from this original cones table. Does that make sense, what it's doing there? So it's picking out things. You can't just say flavor by itself because then Python thinks that was a variable. I never defined a variable flavor. I want to use the text to reference this name of the column. It's with quotes, okay? So there's that. When you say dot select on a table like this, it gives you back a new table. It does not mess with the old one. If I say cones again, it's still the old one. Still got everything there. It's all safe. Okay. The original cones hasn't changed. There's that. But yeah, you can use select with multiple arguments. You can be like cones dot select. Give me the flavor column and then the price column. I don't care about the color anymore. Or give me just the flavor and the color. I've got a credit card. I can buy whatever I want today. I don't care about the price. So this gives you back a new table consisting of just the label columns you asked for. So this is from the cones table. Give me just the flavor column and the color column. There are the rows in that way. And again, it didn't mess with the other one. All right, the other one's still there, but this is making a new table for you to maybe do work on in a simplified way. Okay. So select selects out columns, if that makes sense. Any questions about that one? Select. So a lot of these operations on tables deal with columns, and so that's why I defined it in this way, right? It's always a table. Think of it as a bunch of labeled columns because you're usually going to do column-based stuff. There are ways to do row-based stuff, but it's a little bit harder. Okay, so all these ones are kind of based on column labels. So the next one, the opposite of select is drop. So drop, you give it names of columns, and it gives you back a new table where it's forgotten about those columns, rather than it's picked out just those columns. It's going to lose them. It's going to drop those ones that you say with drop. So you say cones dot, so here's the original cones table. Let's say cones dot drop. Another way to make this table that I just made, a simpler way, is just like take the cones table but drop the price column. That will generate the exact same table, won't it? Does that make sense? So you got multiple options to do the same thing. There's a million different ways to do the same thing in programming. So you got that guy, and you can save this for later if you want. You can be like, all right, that table, I'm going to use that for later. I don't care about the price. I'll call that like cones no price or something. You can always put it into somewhere. That's fine. But the original one did not change. Cones no price. Boop. And so now I've got it called something. I can use that later. But again, the original cones table did not change. All right. So does select and drop make enough sense? You're just selecting out different things. You could have said color flavor and it would have given you those in that order. That's another useful thing. Okay. Yeah, so there's that one. There's also sort. Sort is useful. You say sort and you give the name of a label and it gives you back a new table. It's still never changing the original order of the original table, unless you say that. There's a way to do that. If you say table's name dot sort, the name of the label, it will sort all the rows in that table ascending by default on that column. All right, so it'll give back the whole table still. It'll sort by that column though. So here's how you do it. Dot sort, name of the column, and then by default, descending is a special argument and it's false. So it does ascending, so you can omit that. But if you want it to be descending, you have to change that. So like if this is an original table called cookies, you can sort by the price $sign column, and it will give you back this table where it's then sorted in ascending order by the price. You see that? So we can do the same thing for us. We've got a cones table. So the original one. We can say cones.sort by the price column. And it will sort by default ascending in order of price. So now you can know, like what's the cheapest, what's the most expensive in that order. Does that make enough sense? So this is what you'll use to explore your data before you think about, like, all right, what kind of tests do I want to run? What kind of graphs do I want to make? This is like the basics of all that. This is where we're going, of course. But we got to get through this first. And then cones price. You can also do, there's a secret second argument that's optional. By default, descending is set to false. False just means no in programming. True means yes. So if I say descending equals true, it will now sort by the price column in descending order. So now it's going biggest to smallest, all the rows. All right. It, of course, kept them together. This is still chocolate dark brown 525. It's right there. It's not going to just arrange the column only. It's going to take every individual and shuffle them around. All right. Every row counts as one big chunk of things. So there's that. That's more or less what I wanted to say. Dun, dun, dun. Yeah. Are we ready for the most complicated one I want to show you? The most complicated operation? This is the most useful one probably too. But if we're good, I want to show you dot where. All right. So dot where on a table gives you a table and it picks out rows. Finally we're working on rows. It's going to pick out individuals or rows that match a condition on that label. That's very complicated. All right. But here's a kind of question that you might want to ask. Hey, give me, I only got $5 in my pocket, or I've got $4.99 in my pocket. Give me all of the cones where the price label is set to a value, like all the values in the price table. Or sorry, let me rephrase. Give me all of the cones, all the ice cream cones I can buy where the price is less than $5. That's what I want. You can ask that question with dot where. See how powerful that is? That's something that you can do. Let me show you how to formulate that call, because you can't just say it like that. But that's kind of what we want. All right. So let's go to the documentation as one does. But dot where is the most complicated. All right. It's a little silly, but I will show it to you. I'm going to show you. Let's see. Yeah. I'm going to show you one way to do it right now, but I'm going to show you more options later. I can't show you how to do, like, it has to use, like, you say r dot greater or r dot below. It's really disgusting. But this is how it works. You say the name of a column and then what you want to ask about that column. And it'll pick out the ones, it's called a predicate. And whether there's a yes answer, it will give you back that row. All right. So by default, the question you're asking is it equal to something? If that's not the question you're trying to ask, you have to say something weird with a built-in variable called r. It's like, give me all the cookies where the amount of remaining column values are above 10. That's kind of how you read that. And there's a bunch of different r dot things. Where are those? I will talk about this more in detail later. Where are they? They're down here. There's r equal to, that's the default. There's r above or equal to, r below. But if you don't say r dot anything, just by default, it's going to give you equal to. That's the default. All right, so that's what I want to show you right now. Okay, but dot where gives you a new table with just the rows that meet your condition for that column. Okay. The moral of the story is here's something I'd like to do. You can use dot where to say this. Give me all the cones where the flavor column values are equal to chocolate. By default, it's going to go where it's equal to. It's going to pick out things where it's equal to that thing. Do you see what just happened? It gave me all the rows where the flavor was set to chocolate, where it was equal to it. That's very useful to pick out things you care about. And you can do even more. Like there is a way to do the price, like less than $5. I need to teach you that r dot thing. That takes time. Okay. Are there any questions about that dot where? Kind of see its power? All right. So with that, I just want to show you something cool. I've got a bunch of silly data files that we can pull in. One that's near and dear to my heart as a millennial is the Pokemon data set. So I'm going to use that in some examples in the class. Here's a data set of every single Pokemon. Their names are way over here, like they did it in a weird order, but there's a bunch of different data on all these Pokemon. You got their HP, their Japanese name, their English name, their special attack percentage values, whatever that is, their primary type, their secondary type, like Bulbasaur is grass, etc. Charizard is fire. Which generation of Pokemon games they're from, generation 1, it goes in order. All these fun things. All right, so here's data on a bunch of different Pokemon, and I'm going to import that table, and we're going to do stuff with it, just for a silly example at the end. All right, so I'm going to say table dot, so here I am again in my chapter 3 notebook file. I'm going to say table dot read table, and it's called data. So my data folder, and it's called Pokemon.csv. I want to read that. I want to save it into some name of a table that I can use for later. So I'm going to put it into a Pokemon variable. And so there is my table. It's very long. It only shows me the first 10 Pokemon, the first 10 individuals, the first 10 rows. But we can do things. The name isn't even the first thing, which is funny. If you scroll over, there's a million different labels. We've got, where's their names? There they are. There's the names of these Pokemon. Here's the number that they are in the Pokédex. So you can pick out the Pokemon that you want by its name, for example. Like we love Pikachu, for example. That's a very common Pokemon, right? That people know about in theory. So you can say, you can get Pokemon, you can get Pikachu's stats by saying, give me the Pokemon table rows where the name column, it's lowercase name apparently, where the name column values are set to or equal to capital Pikachu. There's only going to be one that I'm giving back. Does that make sense? So there's Pikachu. Here is him. This is all the rows that have a name equal to Pikachu, and there's of course only one Pokemon called that, right? So apparently they're 50% male. Primary type is electric. Does not have a secondary primary type. This is not applicable, or it's really pronounced as not a number. We'll talk about that later. But he's got this defense. He's base happiness, whatever that means. He's just likely to be happy. It's fun. So there's a bunch of different data that you can look at about Pokemon. But like maybe you've never seen Pokemon before, and you're like, oh, all right, Pikachu is apparently an electric type Pokemon. How does he compare to the other electric type Pokemon? You can ask that question now and get answers. You can be like, all right, give me the Pokemon table then, where the type 1, the primary type of the Pokemon, is set to the value electric. So if it's text, it's between quotes again. here are all the electric Pokemon then. It's going to give you back every single row where the type was electric. And so here's all the different ones. Whee! You've got Pikachu and what he evolves into. And you've got all these guys, and there's more where that came from. If I did a .show, it would have shown me everything. But I'm only getting the first 10 answers back. It's always generating a table for me. I could save this somewhere else and use it later. That's kind of fun. Or you're like, all right, I like this, but I only want to deal with Pokemon that are in Generation 1. Like, I don't care about Generation 2 or onwards, because I'm playing the original games or something. And so you can be like, all right, give me all the Pokemon where the generation value for the column generation is set to the number 1. So here's all the Gen 1 Pokemon. There's 151 of them. I have memorized that, but it's also telling you that because it's outputting the first 10 and then saying that there's this many left. All right. So there's that, and you can save those for later. You can be like, all right, I want to ask questions about just the Generation 1 Pokemon. This gives me back that table. Save it as something. All right, I'll call that Gen 1 now. Here's all the Pokemon from Generation 1. I've called that table Gen 1. I can be like, Gen 1, give me all of the Pokemon. Let's give me back all the Pokemon back where you've sorted them. I want the best team. I want the strongest team. So give me back the Pokemon in Generation 1 sorted by attack descending. You see that kind of question? Like, that's something we can ask right now and get an answer back. I save the Generation 1 table and be like, all right, give me all the Pokemon in that Generation 1 table sorted by the attack column descending equals true. So even now, with this, armed with this knowledge, you can ask questions about a data set and get answers back, which is really powerful. Apparently, dun, 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 where are the values of attack? Is it in alphabetical order? There it is. 155. So apparently, like, these first two are about the same. I would not have expected that. But I've heard that one's popular, right? So this is now sorted by how powerful these Pokemon are. Like, okay, you can have 6 to your team. I want these first 6. You do like .show 6 on that or something. That's the thing. Isn't that fun? But this is kind of all over the place. When you do this, when you ask this question, you get back this entire data set. You get back all these columns. But really, when I see this answer, I really just want to look for the name of the Pokemon. I want to know what the attack value was, why it was so big, and I want to know maybe the primary type of that Pokemon so that I can have like a specialized team or something. So the last thing I kind of want to show you, that's something I haven't talked about yet, is you can chain these operations. You don't have to go through intermediate variables if you don't want to. You can chain these operations because they're all giving you back a new table. You can imagine that this code right now has resulted in a table that I can do dot stuff on. All right, that's what's happening. And so I can do it like this. I can be like, all right, give me this answer, but also after you've created that answer, like this whole thing now, you can imagine it's like between parentheses, this whole chunk of an idea is a table, which I can do dot like show on, do dot select on, whatever I want. So taking this result, I can ask, I only really want, select out in this order, the name column, the primary type column, and the attack column. That's a 2-step process that you can do in one line. Does that make sense? Because this first thing made a table that you can then do more table operations on. So you can chain those things, but it's always going to happen in that order from left to right. The first thing that it did was it sorted the Gen 1 Pokemon by attack descending, then it picked out only the name, the type 1, and the attack in that order, and that's a much cleaner answer. I hope you agree. So that's where you can go with that. That's really powerful and useful, all right? So, with that in mind, I have a question for you to try. If you want to play along, and I highly encourage you to play along, you can go to, you don't have to write this down anymore, but anywhere, but I want you to try it. You can go to this link to get a temporary page, and you can go to our code from class to get that data set. So here's code from class. I'm going to show you exactly how to do this. Code from class. You go to data 8. Here's the data folder that I was working inside of. Here was the Pokemon.csv file. You can click on that. Where was it? Pokemon.csv. And you can download it. Here is the download button right there. Download the raw file. So you can download that. There it is. You can take it. There's on this little page, there's a file browser that you can do the following with. You can take what you just downloaded. and upload it. It's temporary, of course, but now it's there. And now I can say Pokemon equals table.read table, and it's just within the same folder right now. So I just say Pokemon.csv. And so now I have that whole table. Oh, oops, I have to. Also, you want to run this cell now because it's importing data science stuff. So we do that in that order. It'll work. Yay. So that's how you can use that. You just drag it in there, and then you want to run those first two cells. So here, I'll give you this as like a screenshot if you want to get started with that. But my question for you now, can I put this here? I'm sorry, I can't. My question for you is, with this style of ideas, try to find the top 8 Generation 2 Pokemon with the highest defense values. All right, I'll give you a few minutes to try this, and I'll help you import it if you're having any trouble. But you can go to the code from class to get the Pokemon into CSV file. I've shown you all the things that you can do. I've shown you select and drop. Let me actually, the easiest thing that I could do for you right now is let me give you the current version of this file as well in our code from class. I think the computer restarted, and so it's going to take a second. But you don't have to write this down anywhere, but I want you to play around, because that's how you learn. All right. If you refresh our code from class page now, you now have everything that I did. You have chapter 3. So everything that I've written, you have it now. You can see what I was doing. You're going to need, for top 8, that implies sorting, doesn't it? That implies, remember the dot show? You're going to want to show just a few of the top ones, yeah? Generation 2 is going to involve a dot where, get only those ones. And then highest defense is linked to the word top where you're sorting, right? Can you kind of formulate a bunch of dot operations just like that one, where you pick them out in some order and you're left with the top 8 Gen 2 Pokemon with the highest defense? You have that ability to find that out right now, and I want you to try it. All right? So I'll give us like 5 minutes to play around and try that. Maybe a little bit less. Like 4 minutes, let's say. But help each other, please. And, oh goodness. There we go. Also a little timer so I don't forget. I can help you import that file if you have in show. Right way to align the player. Is Pokemon still popular with your guys' generation? So people have done like Pokemon Ghost with them. Oh, nice. So you're already in Jupyter Lab? Yeah. Nice. So yeah, you want to make a new file, and let me see, file browser. Let me go to view menu. Looks like it's not. For the file browser. There, because that's apparently where we are right now. I'm not really sure what exactly you made this file. Is it like in your downloads folder or something? All right. Yeah. So maybe then you already have the CSV file. So yeah, which one do you want to open? Oh, you want to open that one?
Yeah, actually, that one should take me.
Oh, nice. Well, if you just want to open that one, you can just double click it. It should automatically open. But yeah, if you want the data file though, you need to get Pokemon.csv separately. That's another file to that.
Yeah, I saw that one.
That's in the data folder. Yeah. That get it. And for you, because you're working in the downloads folder and Pokemon.csv is just immediately in your downloads folder. When you import it, you don't have to say like data slash. It's just the name of the file is Pokemon.csv. It's the same folder as this number. Where's my read table? Try towards the bottom. If you table.read table, and it's just going to be Pokemon.csv. It's the only thing. It's in the same folder. What is yours? Oh. Anybody else having trouble getting that file? Yeah, definitely encourage you to play around on the big computers. You can log into Canvas, get to that temporary page if you need to. It's very worth it. I'll give you another minute and a half head start, and then I'll show you my answer and how I think about it. Because I think there's a couple different orders that you could do it in. It doesn't really matter, but some things that, like, there is something that has to happen at the very end for sure. But the intermediate stuff can be rearranged. All right, my timer is about to go off. Were there any questions that came up as we were trying this that would not be answered by me just showing you the answer? I want to answer those first and not give everything away. All right, that's my real timer. So here's how I'll think about it. This is kind of I want to teach you this thought process, really. So I want the Generation 2 Pokemon. I got the Generation 1 Pokemon in this Gen 1 variable. So I'm going to do the same kind of thing to get the Generation 2 Pokemon. Yeah. So start with Pokemon, but don't give me Generation 1, but give me Generation 2. Yeah. Give me Generation 2. And then I want the highest defense of any of those Pokemon, and the label for that one is just called defense with the lowercase d, I believe. Should be there. There it is, defense. And so I would like the highest of the defenses. So give me the Generation 2 Pokemon, then I've got those. Give me the highest defenses. So that's going to involve sorting, right? I want to now sort whatever I've got, just sort the Generation 2 Pokemon by defense. Sort by the defense column where it's getting smaller. I want the bigger ones at the top. So sort in descending order. Descending equals true. So now I've got I've got every single Generation 2 Pokemon sorted decreasing by their defense. Does that make sense, what I've got there? And I only want the top 8 of them. And so I can do a dot show with a special number, the number of how many I really want. Does that make sense? That'll work. That'll do it. Another thing I could do, because this is going to look a little bit ugly, this is correct, but usually you probably want to play this game as well with a select, like just give me their name and maybe their defense value or something. Oops. So before you show it, like just here's the answers, but select out only their name and their defense value. That's all I really need here. It's a cleaner answer anyway. Does that chain of ideas make sense to us? Are there any questions about that? Some of these can be reordered. For example, the sorting and the wearing here don't matter. I could sort by defense first. I just want to kind of have you think about what the difference here is. This would also give me the same answer. Ta-da. But it's doing it in a different way, right? Now it's first sorting every single Pokemon by their defense descending, but then it picks out only the Gen 2 Pokemon. It's already been sorted, though. Does that make sense, the difference in order there? The select cannot happen before the sorting. Or sorry, the select can't happen before the dot where on generation. Because if I did it in this way, I would get an error. Can anybody see why? Why this wouldn't work? It's a very long error. But if you scroll down to the bottom, usually it tells you what it's trying to say. Generation not there. Do you see the problem now? after I did the sorting, I took just the name and the defense, and then I'm trying to, now I got a table with just names and defense columns, and I'm trying to find generation 2 of all those things. I lost the generation column when I did the select. Does that make sense? So I can't do it in that order. It has to happen before. So there is some things that you can change the order of, but there are also some things that you can't. Like the .showAid, of course, that has to happen at the very end. That involves displaying it. That's the last thing we care about. Okay? And that is kind of the answer. One of the answers. Are there any questions about that? See it? So definitely play around with this once you get home. I think this would be a great way to study, practice, or during the lab time. But yeah, that's most of what I wanted to say today. Yeah, the last thing I want to do is, I'm done. I have just a little section sometimes for just things that I'm required to teach you that weren't part of the lecture or aren't part of the textbook reading that you're going to need for the assignment. So here's the section name, miscellaneous things I need to teach you today. And then I'll release your first assignments and I'll let you work. So, okay, the last things I want to teach you is there's a way to display things. It's called the print function. And you can put text or even numbers in the print function. You say like print hi mom, exclamation point. And Python doesn't care if it's single quotes or double quotes. This will print the answer, all right? It will print an output to the screen. It's a little bit different, though, to just saying hi mom in quotes by itself. So you see how in the output there's quotes still here? That's implying that something weird and different is happening there. What print does is it forces output to appear. So this is something I can do now. By the way, Python does not care about quote numbers. So I can do single quotes as long as you're consistent. It doesn't care. So I can print hi mom and have another line saying print will also see this in the output. And I kind of needed double quotes for this one because of this apostrophe. Because if I use single quotes, it gets confused about where the text ends. It's like, all right, you just said we, and then you started typing other things. That's how it's thinking. So I needed double quotes for this one, just because I wanted to have this in the string and in the text. So if I run this is going to be the exception to the normal rule of I only see the last thing output. You see that? Print forces output. So when it runs this line, it forces that to appear in the output. When it runs this line, it forces that to appear in the output. See that? So that's something that's necessary. Print can take multiple things. It can take numbers as well, 42, 43, 44. And what it does is it prints them with spaces to separate. And that is a way that you can force intermediate output. You could be like x equals 42, print the value of x times 2, in addition to doing x times 7 plus 42 or something. I don't know, plus 11. So now I see two outputs. Does that make sense? I've forced an output here with the print. That's a way to display multiple things at once. That will be necessary for an assignment. Questions about that? This is a print function. It forces output. So it's not just the last line that's outputting things when you say print. We good with that? That's it. That's all I got for us in terms of lecture stuff today. The last thing I want to do before I let you go off and work and take take a break if you need to, is I want to schedule due dates for these guys. The order is like this: lab 1, then homework 1. And I'm honestly just going to release every assignment so that if you want to get ahead, you can. It can only help you. But here, it's going to be on our modules page, and here is... you already know how to get the first assignments. I already released them, right? But here, you can have all of them now if you want. The order of them is supposed to be this. If you go and look at this big later once I upload stuff. But you can get started if you want. I'm not setting due dates for any of those, but I'm setting due dates for lab 1 and homework 1. All right, from now on, once I finish something. So they required up to chapter 3. We've just covered now up to chapter 3. So let's set due dates for those real quick, and then the rest of the time will be yours to work and to ask questions. So remember that my due date policy is things are due at 5 p.m. unless you have an extension, and I like to give you at least a week to work on things. So let's say I will have the next assignment due, lab 1 assignment due, let's have that be due on next Wednesday, the 21st. All right, so that's when I'll make lab 1 due on the 21st. Remember, 5 p.m. And then we'll do the other one. The homework one's supposed to come after that. I'll make it be due on a day after that. Let's do the 23rd then. So you have some time in between, but definitely get started on both. So a week and 2 days. So Wednesdays and Fridays will tend to be when I want to have things due, I think. So the 23rd then will be the homework one's due date. Okay? So that will be the schedule there at 5 p.m. again. All right. That I can click save, and so you should be able to see those due dates as well in Canvas. But hopefully you already gotten started, and it won't be too bad. But just don't wait till the last minute, okay? And I've shown you how to upload. Let me know if you have any trouble with any of that. But I think that's all that I've got to say. Are there any questions about anything we talked about today before I let you work? All right, the rest of the time is all yours, and I will work on giving you everything we did today.